So now let's extrapolate this idea of the p-values that we discussed in the previous app to this proportion of population problem, right? So now, again, we have a null hypothesis. In my case, you can see that null hypothesis is that proportion of blue disks in my population is 50% or larger. I have exactly 50%, so it means that my null hypothesis is true in this case, right? Now, I compute the sample proportion, and I got a proportion of 40. And the question is, how likely, if my null hypothesis is true, how likely I can get, if I repeat this experiment again, how likely I will get 40 or more extreme? What will be more extreme in this case? I expect to have 50 or more. So any value smaller than that will be more extreme, right? How to compute a p-value? Well, what you see here, it's a possible distribution of possible expected sample proportion if null hypothesis is true. So if null hypothesis is true and if sample size is 20, then this is possible distribution of the proportion of my samples. Okay. And then this is exactly where my sample is. What's the chance that the next sample I take will have 40% or smaller? That's exactly this area, right? So I can simply compute area on the left, or I can use a CDF function for that, right? And then that gives me a p-value. And you can see that the p-value is 18.2%. So in this case, the p-value is quite large. So I do not reject null hypothesis. I say, okay, it's quite likely. So if I assume that it should be 50% or larger, and if I take a sample size of 20, so 40% doesn't seem to be that extreme, right? So I take a new sample. So now you can see that my sample is perfect for the null hypothesis, almost perfect, because it would be perfect if I used both tails, but I use only one tail. So I expect to have it 50% or more. I got exactly 50% in my sample. So the p-value is also 50%, right? So that's exactly the area on the left in this case, right? So I take one more. You can see now it's even better sample. So now I expect to have 50% or more. I got 60. So it's even better for my null hypothesis, and you can see the p-value is also pretty large. So it's not extreme sample for my population. So chance to get 60 or even less, because less will be more extreme, right? Will be almost 82%. Okay. Now, when to reject null hypothesis? Well, that's a bit controversial question, because many people, for example, say, okay, if p-value is smaller than 5%, we reject it. Okay. So why it's not a good idea to use always this fast 5%? Because, I mean, you see that the null hypothesis is true in this case, right? But if I start taking a lot of samples, you can see that, look, 1 out of 17 had p-value smaller than 5%. So I rejected my null hypothesis in this case. So you can see that in 6% of the cases in my particular example, I rejected my null hypothesis, but it was wrong. I know that null hypothesis is true. It's me who made this null hypothesis, right? So I know it was a wrong decision. So it means that every time you work with this value, you have 5% chance to make a wrong decision. You have 5% chance to reject null hypothesis, although the null hypothesis is true. And sometimes this chance can be pretty large, especially, for example, if you think about effect. For example, you make a medicine that treats a certain disease, and rejection null hypothesis means that you believe that the medicine works, so you have an effect. And then you have 5% chance to observe an effect which does not exist. So it means that you have 5% chance to give a hope for people which actually that medicine works, although it doesn't. And that's a pretty big chance, right? So therefore, don't use this 5% rule. Always estimate this limit, the significance limit, depending on the risks. And also always provide the p-value so people can self-assess is it indeed extreme value or not. Okay. Now, this direction of extremeness depends on the hypothesis. For example, if I use right tail, you can see there, that means that it's 50% or less. And now you can see the p-value is much larger, although I have the same sample size in the same sample here, right? So you can see that the idea is following. If you expect that your proportion should be 50% or less, right? So it means that every time you have a proportion more than that, it's more extreme. So the direction of extremeness is to the right, because on the right you have larger proportions. You got proportion 35, and then you expect to have it less than 50. So this is okay, but all these values will be more extreme. So therefore, the p-value, you compute p-value using the right tail, and that's why the hypothesis is called the right tail hypothesis. If you use left tail, then it's other way around, right? So you expect that the proportion should be 50% or larger, that anything that be smaller, the small proportions will be more extreme. So you have the left tail hypothesis, right? And then both tails, it's when you have exactly in between, and then you can see that you have, for example, if your proportion is 65, so anything, you're 65, it means it's by 15% larger than 50, right? So anything that 15% larger or 15% smaller will be extreme, because now you assume it should be exactly 50. So any value which is larger than 50 and any value that is smaller than 50 will be equally extreme for that, okay? So that's it. Again, play a little bit with that. Make sure that, for example, sample size doesn't change this one. So if you work with 5% significance level, you always have 5% chance to reject a correct null hypothesis, regardless sample size, regardless proportion. It's something that is sort of you defined, okay? So this is a chance to make a wrong decision, a chance to see an effect which is actually not present, okay? So play with the app and hopefully get a better understanding of this.